Okay, you have some homework in Bayes' rule. Let's quickly review what we did. So here we talked about the color blindness, and we had an event B, which is a man, and the B complement was a woman, and together they make up the whole sample space. And we saw that if we have another event A, which in this case is being colorblind, that we could write A as, remember we talked about a partition. So we talked about something like this, and here we're partitioning the entire set S. We're partitioning it into 3 pieces, here, here, and here. And in the first example, though, we are partitioning S just into B and B complement, where B is male and B complement therefore is female. So we see that if we have a set A, like that, that A can be written as the union of the part of A that intersects B with the part of A, and the part of A that intersects B complement. And we saw that because these two are disjoint, that we can change union into plus. And then these probabilities are calculated from the previous problem set. So I don't know where these numbers come from exactly, but they came from the previous problem set. So it's this one and this one gives us this answer. And then we said if we have a partition, much bigger more sets in the partition. So this might be S1, and this might be S2, and so on. So we can have actually K pieces. Then if we have some set A, we can write it this way, as the union of this piece, and this piece, and this piece, and so on. And then since, again, those are disjoint, we can change the unions to pluses. And this is another picture. And then we also said that we can rewrite each of these pieces here, like this piece, and this piece, and this piece. We saw on the board that we could rewrite each of those like this, and so on. And so we get this expression here. And then they gave us this problem, and I was not sure about the meaning here of these things. What does this mean in English? I'm not quite sure. But here, this does form a partition. G1, G2, and so on forms a partition. So they will be the S's in the previous screen. And that will give us something like, here are instead of S's, now we have this, and we have this. So they are the partitions. And so we get this expression for the probability of A. And from that table that is not that clear, we can pull out these probabilities to get an answer for the probability of A. Another example here is let's take a look at this. They call it a false positive. is the event that the test is positive for a given condition, given that the person does not have the condition. So they're talking about a false positive let's consider this scenario. So a cancer screening test. So we're talking about a test. So in this case, it's a cancer screening test. So you get, maybe they draw your blood and then they check. And so then the condition, supposedly the condition, is, for example, having cancer. So positive means the test says you have the disease. Doesn't mean you have the disease. It means that the test says you have the disease. So false positive means that even though the test says, I don't know how to fix this, even though the test says you have the disease, you don't have the disease. So that's what we mean by false positive. And false negative means that even though the test says you don't have the disease, you actually do have the disease. Okay, so we're talking about that kind of situation. So we'll talk about that in a moment, but let's talk about this for a moment as well. So this is what we call Bayes' rule. So let's see if we can figure out where this comes from. Okay, so let's review all of this in the text. So here we have the color blindness. We have B, the person selected as a man, BC, the person selected as a woman. We said that we can write A like this. And they filled this in, and we got that, these numbers. We talked about the words mutually exclusive and exhaustive. That's what a partition is. It has to be mutually exclusive and exhaustive. So if we have sets S1 through Sk, and they're mutually exclusive and exhaustive over the entire set S, then we're call that a partition. Then we can write A like this. Then we can write probability of A like this. Here's a picture again. So this law of total probability means that you can write this. Law of total probability means you can write the probability of A like this. So we saw this expression already, so I won't go through it again. And we saw this example, and we used the law of total probability here. But really, I have to say that, this table is just not clear. So I'm not clear that the probability of G1 is equal to this, and I'm not clear that the probability of G1 given A is equal to that. I don't consider it clear. Okay, but anyway, we get an answer. And they call this the unconditional probability. Or we just call it the probability of A, but they also call it the unconditional probability. So going to here, suppose we want to know the probability given A. Suppose we want to know the probability given A that it comes from one of the partitions. So that would be going back to here, and what? Well, going back to here, the partitions are here. So we want the probability that it's, for example, A, whatever A is, like this would be A, given that it comes from this one of, like, say, this partition. So given that someone's in this age group, what's the probability of that? Is that what they said? Let me just check that. Yeah, no, the other way. Given that they're here, what's the probability that they come from one of the partitions, from one of the age groups? So, because that's what it says here. Given that they're there, what's the probability that they come from one of the partitions, or one, in this case, one of the age groups. So where does this formula come from? They say, from, so suppose we want to calculate this. Where does this formula come from? Where does this come from? So they say we know that this, which is this, is equal to, by definition, this over this, right? This is A to the right of the bar here. So that's the probability of A is on the bottom. And then what we have is the probability of A intersect S sub I on the top. So we can just say, okay, what is the probability of A? What is on the bottom? We just finished saying that the probability of A is here. The probability of A is equal to this. We went through a lot of work to get this. The probability of A is equal to this. So, but on the bottom of this is the probability of A here. So we have to put that long thing in the denominator, which is here. So that's where the denominator comes from in this expression. And the numerator is the probability of A intersect S sub I. But we know that that's just this. This is just the simple thing. Well, anyway, it just comes, I've written it on the board many times. This is just basically the definition of conditional probability, and then we brought the denominator over to the other side. And go back in your notes and check that. This is very simple. And this we worked on a lot to get this. So we get that the top part is this, and the bottom part is this whole thing. That is Bayes' theorem. So in class I said it was going to be a little bit of work to go from what we already had, which was this, to Bayes' theorem. But actually, I forgot, but it's actually very simple, because we just want this. We know it's equal to this, but the bottom is this part here, and the top is simply this. So that is Bayes' theorem. But as I pointed out, notice that the given part is A here, but on all these terms, even though there are many terms, it could be a lot of work to calculate all of them, but all of them have the given part as not A, but as the partition part. So we reversed S given A to A given S. Well, we have to do a lot of work here, but at least we reversed the order. So that may make it easier. And then that can just be written like this. In other words, the bottom part was a long string of pluses, and that can just be rewritten like this, as a short way of writing it. And the top part is exactly the same as it was, as we just saw it in the book. So this is an expression for Bayes' theorem, or Bayes' rule. It's just exactly this expression here. Now, there's a certain kind of language that they use to talk about this theorem, which sometimes, well, for me, for a long time, it really kind of confused me. But they use the word posterior probabilities, and they call the subpopulations states of nature. So this really has to do with a particular way that they're using this, but I'll just explain it a little bit. So the posterior, they call it posterior probabilities. So this is called a posterior probability. 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 So just the probability of A without given S1, just the probability of A without given S2, that's just called the prior probability. So prior means before. So before being given S1, what would you say is the probability of A? That's called the prior probability. So just P of A is called the prior probability of A. But this is not the prior probability of A. This is P of A given something else. So that's called, so we're given something. So posterior means after. So after being given S1, what's the probability of A? After being given S2, what's the probability of A? So so this kind of expression is sometimes called the posterior probability. So not just the probability of A prior or given nothing, but given S1, given S2, given S whatever, that's called the after being given S1, S2. So that's called posterior, because posterior means after. So these are referred to as posterior probabilities. And as we said before, the S1, the S2, the S3 are sometimes called subpopulations. They're also called states of nature. So calling it a state of nature is probably for some particular use of this theorem and not necessarily general. In other words, you don't have to always use that language. Okay, so let's go through a few exercises that occur in the book. Okay, let's look at this. So a sample is selected from one of two populations. So we have two populations. For example, we could have the population of all male APU students and the population of all female APU students, just for example. And the probability of, let's say S1 is males, and the probability of S1 is 0.7. That would mean that 70% of APU students are males. And the probability of S2 is 0.3, would mean that 30% of APU students are female. The probability that an event A occurs, given the event S1 or S2 has occurred, are as follows. Let's say that A is that the student will stay in Beppu during a break. So this would mean that given that the student is in S1, that is, given that they're male, the probability that they'll stay in Beppu is 20%, and this would mean given that they're female, the probability that they'll stay in Beppu is 30%. Okay, so let's try to do these exercises. So first of all, where is it? So exercise 1. Use the law of total probability to find the probability of A. Okay, so what does that mean, the probability of A? The probability that a student will stay in Beppu. So this is regardless of whether they're male or female, just the probability of any APU student staying in Beppu. So going back to that language of prior and posterior, this would be called a prior probability. It's not given anything. So if we want to find the probability of A, we can use the law of total probability. So I took a little screenshot of that. Go back to the problem and keep the screenshot available. Okay, so we want the probability of A. And we're given this stuff here, as well as we're given this and this. So the partition here is just going to be S1 and S2, right? We're dividing things only into S1 and S2, so we don't need all these terms from here on out. We don't use these terms. These are not being used. So we only need these two. So the probability of A is given by this. And so the probability of S1 we were told was 0.7. The probability of S2 we were told is 0.3. So we have this and we have this. And then we also have probability of A given S1 is 0.2, and the probability of A given S2 is 0.3. So we have all the terms. So we can just put them in and calculate this here, and that's going to be the probability of A. And if you do that, apparently the answer is 0.23. Okay, let's go to the next problem. Use Bayes' rule to find the probability of S1 given A. So remember that the original data was given in the form of A given S1, A given S2, but they want to reverse that. They want S1 given A. So what would that mean in terms of the actual problem? So A is that the student stays in Beppu during the break, and so given that they stay in the during the break, what's the probability that they're male? So that's this question. So this might seem hard to find, but we can use Bayes' theorem, and it will allow us to reverse these. And we see that we were given this, in other words, the reverse case here and the reverse case here, so we can probably calculate this from Bayes' theorem. So going back to the previous section, here is Bayes' theorem, and I'll just take a screenshot of that and go back to this problem. And we want to find P of S1 given A. So like this, P of S1 given A. So this is SI. So we'd put S1 here. That would be S1, and this would be S1. And then we'd have to use S1 and S2. We don't need this again because we're only partitioning into two sets. So this disappears. So we just need these, and we're given these, like A given S2, that's here, and we're given A given S1, it's up above here, I won't show it, but it's there. And we're also given this and this. And notice, by the way, that this is the same as this, because we're talking about S1, so SI becomes S1. And this becomes S1. So anyway, this term and this term are actually the same. Anyway, regardless of that, we can fill in this, this, and this, and that will give us the answer. So I'll let you do that. And then we can do the same thing for S2. Then we would use S2 here, A. This would be S2. This would be S2. This would still be S1, S1, but this would be S2 and S2. We are given all of that information, so I'll let you fill that in. Apparently the answer is that. Okay, let's look briefly at the second one here. So they say when an experiment is conducted, one and only one of three mutually exclusive events can occur. So I gave an example like that in class where I said this is person's beer preferences Kirin, this is Heineken, and this is not Kirin and Heineken, anything else. So we can divide up the sample space into these three mutually exclusive events, or it could be any other example of mutually exclusive events. But we're saying that there are only three of them. And we're also saying that they are exhaustive. That is, when you take the union of all of them, you get the whole sample space. And then they tell us that the probability of S1 is this, of S2 is this, and S3 is that. So one thing that you should check is that these probabilities should add up to 1, otherwise they're not exhaustive. The probabilities in an event A occurs, so this is some other event, given that event S1, S2, S3 has occurred. So here we're given these kinds of conditional probabilities. If A is observed, use this information to find the probabilities here. So we want the probability of S1 given A, but we're not given that. We're given A given S1, but not S1 given A. So you're going to need Bayes' rule or Bayes' theorem. Okay, so I'll let you work on that yourself. Law of total probability. So once again, that's this section here of the text, or here's the actual law. So I'll put that up here. A population can be divided into two subgroups. So that means we're only going to have a partition with two sets that occur with probability 60 and 40%. So that means the first one, S1, is probability 60, and the probability of S2 is 40. An event A occurs 30% of the time in the first subgroup. So how do we express that? So given that we're in S1, the probability of A is. So it's the probability of A given S1 is 30%, and the probability of A given S2 is 50%. So not this way, but the other way around. A given S1, A given S2. So that's the kind of information we're given here. What is the unconditional probability of the event A? In other words, what's this? This is called we called this the unconditional probability of A, which actually it's just the probability of A, but they just want to emphasize that there's no conditional here. So they call it the unconditional, but it's just the probability of A. So what's the probability of A? Well, it's this and this, and we only have two terms because we're only partitioning into two sets. So we are given, hopefully, we're given the probability of S1, that's 60%. We're given the probability of S2, that also is 40%. Event A occurs 30% of the time in the first subgroup. So that means given the first subgroup, that means given S1, the probability of A, so that we're told is 30%, and the other one, I guess, here is going to be 50%. So we have all these pieces, so we can figure out that. So I'll let you work that out. Okay, now here's a kind of more practical example. So we're going to have to try and sort of rewrite this thing about violent crime as some kind of Bayes' theorem or Bayes' rule question. So it says city crime records show that 20%, so you're going to have to sort of parse this sentence or these sentences or this problem. And since we know that this is in the Bayes' rule section, we know that we're probably going to have to use Bayes' rule or the complete probability rule. Probably there's going to be some partition involved here. So let's just assume that that's true and sort of look for it as we read the problem. So city crime records show that 20% of all crimes are violent and 80% are nonviolent. Okay, so I can see right there, maybe the partition is that violent versus nonviolent crimes. So you might say, is that exhaustive? Yeah, it's if something's a violent crime or it's a nonviolent crime. So that is exhaustive, and they are mutually exclusive also. I think that's pretty clear. You can't have a crime that's both violent and nonviolent. And I think this part we can ignore, involving theft, forgery, and so on. 90% of all violent crimes are reported versus 70% of nonviolent crimes. So if there's a violent crime, it's probably reported to the police. In fact, 90% of the time, it's reported to the police. But if it's a nonviolent crime, it's not as highly reported. So only 70% of nonviolent crimes are reported. So let's say, we're not sure, but let's say that the partition is violent versus nonviolent. All right, now let's keep going and read. What is the overall reporting rate for crime? So this is probably, by overall reporting, they probably mean this picture. So we're going to partition violent. This is supposed to say non-violent. So violent versus non-violent, and these are the reported crimes. And we're trying to figure out, they ask us in the first part, what is the, right here it says, what is the overall reporting rate for crime? So we want the percentage of reporting, or the probability that a crime is reported. And so that's, so here this is what we've been calling A, not R, but I called it R in this case. So which should I call it? I'll call it R. So that's, we want the probability of R, and then we do this. Now the partition only has 2, so we only need this part here, right? There's only V and non-V. So S1, sorry, is violent, and S2 is non-violent. So hopefully they tell us the probability of violent and the probability of non-violent, and hopefully they tell us, given that it's violent, this is S1, violent, this is R. Given that it's violent, what's the probability that it's reported? And hopefully they tell us, given that it's non-violent, what's the probability that it's reported? And from that, we can calculate the probability of R. So do they give us all that? Well, I think they did. So I'll let you check that. I think that's all given right in here. So we had to kind of translate that question into what I guess we called it the total probability rule. Okay, next one. If a crime is in progress is reported to the police, what is the probability that the crime is violent? So it's a little hard to discern that, but that's a given question. So where's the given part and what's the other part? So what is the probability that the crime is violent? That's the not the given part. They're saying given that it's reported, what's the probability that it's violent? So they are asking a question like the probability that it's, given that it's reported, what's the probability that it's non-violent? So this kind of question. Now, I think before we were, or in the problem they gave us things like R given V, but here we want the reverse order. So we're going to need, because what we're given is the stuff in the reverse order, so we're going to need to use Bayes' theorem, because Bayes' theorem allows us to use the things in reverse order. And those are the things we were given, so we can fill all those in over here in Bayes' theorem, and then do the whole calculation, and that will give us this. So I'll leave that explanation like that. Okay, and the other problem should be similar, so I'll let you work on these in the homework.